probably like plus hours.
Let's get started.
Plus like, now we have that.
So, a number of announcements. So we have a concept due, and another one is coming. It'll be due the Thursday after spring break. Okay, it'll not be a longer assignment, so we'll get a break. But I feel like looking at it during the break. You're encouraged. Then we have some break. Yay! The week after break, I will be on travel. So I have a question choice for you in terms of how we want to do this. We could do it in two different ways. One is we can just do it, Back to the Future. Here we are in 2020, doing remote class, and have a Zoom lecture. Alternatively, you can watch the lecture Vintage 2012, which somebody put on YouTube, we didn't, and then use this as a time as a flipped classroom to talk about the homework or talk about the lectures and just have a discussion. What would you prefer?
The second.
The latter works better.
How many would prefer the former, meaning I will do it as, a remote lecture. Okay, 2 people. Okay, so we have, and then how many people would prefer, or you watch the lecture on your own, and then we'll have a discussion section.
Really? But the 2x.
A lot of people didn't vote.
I'll send an anonymous online poll, and then you guys can decide. Okay. All right, very good. All right, so last time, again, we were talking about this very important idea of conservation laws, conservation of some kind of stuff. And the general form, differentially, is that at any point in space, the local density of that stuff can change because it's flowing, so it can converge or diverge onto that point, or there's some rate of change of that stuff that is created or annihilated in some way, okay? And so if the stuff inside the volume is the integral over the volume of the density of stuff, that's the total amount of stuff inside some volume, it can change due to current of that stuff into the volume, or minus the current out of the volume, plus the rate of creation of that stuff inside the volume. That's the general form of a conservation law, dynamically, okay? And so we had a number of different examples we've been looking at in electromagnetism. Charge is neither created or destroyed, so this right-hand side is 0, and this is the continuity equation as for charge that tells me that charge can only change in a certain place because it's moving from one place to another. There's current. Energy in the field satisfies Poynting's theorem. Which tells us that how the local energy density in the field is changing relating to the flow of the energy through the Poynting vector. So U here is the energy density locally in the electromagnetic field. And energy in the field can either be absorbed by matter, or it can be transferred from the matter to the fields. So energy can be put into the fields from the matter. And the rate at which energy is created in the field per unit volume is minus J dot. Yeah?
So for our charge equation, is charge actually completely conserved? Because like we learned that mass and energy are conserved, and then we learned that you can transfer between them and stuff like
Right.
that. Is charge like actually for real conserved?
Yes,
Okay.
as far as we know. I mean, everything is, You can ask God at some point, but I don't know, yeah.
And then as far as we know, is implicit in everything you say.
Yeah, that's always implicit, yeah. Okay, and then we talked also briefly about the fact that the electromagnetic fields can possess momentum. That is to say, the rate at which momentum is transferred from matter to the fields is minus the rate at which momentum is transferred from the fields to the matter. The rate at which momentum is transferred from the field to the matter is the force on the matter. Minus that is the other way around, the way momentum is transferred from the matter to the field. So minus the Lorentz force per unit volume is the rate of creation of momentum in the field per unit volume. And when we use Maxwell's equations, we find this equation where G is 1/4πc E cross B is the momentum density. And T is a tensor. It's a tensor because the stuff that's flowing is a vector. And the direction of flow of the stuff need not be the same as the direction of the stuff itself, which is why there are two indices there. And written as an outer product, this is that. And that's known as the Maxwell stress tensor. It's known as that because it has the form from continuum mechanics of stress and strain. Yeah.
For the momentum equation, is that rho E on the right-hand side, or?
Yes, that's a rho, sorry. That's the Lorentz force per unit volume. Yes.
Do those E and B in the Maxwell stress tensor have different indices, or are they just the same E and the same B?
Well, so if I were to look at this as a matrix with components, that's what the outer product means. So on the diagonal, I have this, and then also another term, and in the off-diagonal terms, I have things like EXBY and EXBY, etc. Okay? So these are the components of the tensor. Okay? Very good. It's not irreducible because it's not traceless. Okay, but that's sort of neither here nor there. Right, so, and finally, I'm going to just be lazy and write if I cross the position into the force, this is the torque per unit volume. And the torque per unit volume, the torque is the rate at which angular momentum is being imparted from the field to the matter, right? So minus that is the rate at which angular momentum is transferred from the matter to the field. And it flows, and I have to cross everything here, and I can talk about the angular momentum density, which is the position crossed into the E and B at that position. Okay, and you have some thoughts about that in your homework. So again, the point here is that the fields are becoming an entity unto themselves on an equal footing with matter. It's as much stuff as matter is stuff. And in our modern understanding, everything has a kind of corpuscular quantum nature. The particles of matter are sort of on the same par as the particles of the field. They just have different properties. They can carry momentum, they can carry angular momentum, they have energy. They may or may not have mass. Let's say la vie, ask God about that one. But we see this already from our formulations of the theory that if to the degree to which we think about the fields as physical entities, the quantities that we think about in mechanics can be transferred from the mechanical system to the fields. And they then possess those physical quantities. They can give it back. The energy can be taken from them, it can radiate, or we'll talk about radiation in a moment, or soon, into the field and then transferred to matter, right? I mean, or emotion, I talk into the microphone, it makes radio waves, it goes into that and then pushes on your ear. So and you hear something and you get information. So that's physics. Okay. All right. Very good. All right. So let's now continue and think about, as we know, the full implications of Maxwell's equations. And let's, consider what Maxwell did is, he didn't call them his equations, but my equations.
What did he call them?
I don't know. The equations.
The 18 equations of electromagnetism.
Yeah, yeah, exactly. The ones that might be right, I think is what he called them. So let's consider Maxwell's equations in vacuum. Let's say where rho and J are 0. There's nothing else, okay? So we can write down the Maxwell's equations, which now says del dot E is 0 rather than 4 pi rho, and del dot B is 0, and del cross E is equal to minus 4 over C dB dt, and del cross B is equal to plus. Now there's only displacement current, there is no conduction current, okay? So those are the 4 equations in vacuum. They're a set of 4 coupled partial differential equations. And we'd like to solve for E and B as a function of position and time, given these set of coupled PDEs. So first thing we notice about them is, of course, what we see once we added the displacement current is that a changing B creates a curling E, but that curling E is changing in time, which will then create a curling B, which will create a changing, and it goes back, and it just keeps going like this. And so we see from the equations of motion themselves, the fact that we can get a propagation of E and B through space, time. Yeah, Don, you had a question. Yeah.
I was gonna say, we're being a bit loose with terminology, right? We're not actually saying that time zero changing field creates the other field, right? It's just they correlate or something.
Well, yeah. Well, I'm saying if I had no, if in some region of space, if all of a sudden, in the same way, let's say they create is a loose term, is to say that it is the source for,
Okay.
right? So instead of having, in this case, conduction current, I could say the current is the source of the magnetic field. In that sense, the current creates the magnetic field. That's what I mean. It's the source. Yeah.
So like in vacuum, the permeability and the permittivity are also equal to 0, right?
There is no permeability. There is no, the permeability of free space is 1, and so it is. This is CGS. There is no such thing as V naught and epsilon naught. That does not exist. That is a figment of our imagination of the idea of the ether. There is no ether, there is no permeability of free space. That is a figment of your imagination.
Preach.
All right, we are going to continue. We'll come back to that. Well, when we next, after spring break, we'll talk about permeability and why people thought about where the name, the permeability of free space came from. Because we haven't talked about permeability at all. Permeability is a property of matter. Matter, free space, now, that is maybe a little bit of a lie because, of course, in the quantum world, there is no real vacuum, okay? And so we can come back to that, but no quantum, okay? All right, here we are. We're back to this. So we want to solve these equations. How do we do it? Well, the way, when you have coupled ODEs, the way, or PDEs, what you do is you take second derivatives to try to uncouple them, to have separate equations for E and D. So the standard approach that you should know over and over again how to turn this into an uncoupled equation is take a second derivative. So I'm going to take another curl of E. Right? And everyone remembers what this is, right? What is it? Yeah. It's the gradient of the divergence minus the Laplacian. You will remember that. I command thee. Remember this. Okay? That is the one vector identity you at command class should know. You can derive it in a couple of lines if you remember your epsilon IJGs, but don't bother. Just memorize this one, okay? Just memorize that. All right. So with that, in free space, this is 0. Okay? And that is equal to, according to Faraday's law, and the fact that I can switch the order because of smooth functions of the derivatives, put the curl through the derivative of the partial derivative of time, and then using the modified Ampere law, I get equals to minus 1 over c squared, the second derivative of E with respect to t. Okay? And so I've uncoupled E from B in having an equation of motion directly for the electric field, which says this.
So you just substituted.
I substituted this equation into here and took the second derivative. Okay. Yeah.
It might be dumb, but it seems weird to me that we only had to use 3 of the Maxwell equations to do this. Like, this is such a, the idea that the
We only had to use 2 of them.
Well, we used del.
Oh, yeah, we did. That's right.
We just didn't use magnetic lines.
Yeah, this company. Now, they're going to be interrelated in a moment. We'll talk about the constraints a little bit more. Hold that thought, but it is an important one. And we could do the same thing by taking the curl of this equation, doing exactly the same thing. And when we do that, we get this equation. We would use and this was the magic that Maxwell discovered himself when he looked at these equations and found that the thing that appeared here was 1 over the speed of light squared. I mean, C didn't appear in Maxwell's equations. Things like the permeability of free space did, which were based, as you may and probably not remember from the very first lecture, of how the units were developed in terms of, how to think about the different ratios of the different forces, and they found that those different constants related to the speed of light. Okay, we have put the speed of light in there by hand in order to be consistent with the empirical laws of ampere and coulomb and Faraday, okay? Right, so, yay! What we see here is that each component of E and B satisfy the wave equation in 3 dimensions. So just to remind you, in 1D, say, along Z, the wave equation for a scalar psi is that, where V sub p is known as the phase velocity. We'll come back to that to remind you of some of those things in a moment, okay? So what we have over here, for example, is that, dx squared plus dy squared plus dz squared minus 1 over c squared d squared by dt squared of, say, the x component is 0. That's what I mean. It's a wave equation in 3D, and every component, when we write it as a vector equation, we're saying every component satisfies the same wave equation, okay? And what we see is that the phase velocity is c by this equation, okay? Now, going back a little bit to your points, Tristan, what we have here is 6 PDEs, okay? But those 6 PDEs are actually not independent from one another because they must also be consistent with Maxwell's equations, okay? So we have constraints. We have that del dot E is 0, which means that the 3 components of E are constrained in some way. They can't be just any old 3 components. They have to have 0 divergence everywhere in space, okay? So that means that for E, we really have 2 degrees of freedom. DOF, degrees of freedom for E. And similarly for B, because we also have that delta B is 0. Yeah.
This might be a bit of a nuance or a detail, but are we enforcing those conditions because we used them in deriving these?
No, it's just because they're true.
It's just because they're true.
Yeah, it's also true that we couldn't have gotten the equation without this, but we can't forget that we used it. So there are solutions to this equation which won't satisfy this. But the only ones that are physical in free space are the ones that satisfy that. Moreover, E and D, even though we decoupled them here, they're actually really coupled. So it must be the case that the kernel of E is not independent. I can't have just independent solutions of E and D. They have to be related to one another through Maxwell's equations. In particular, the kernel of E must be equal to the local rate of change of B in this way. And similarly, it must always be true that the kernel of B is 1 over C dE dt. Which means that once I have a solution, say, for E, I can solve for B. It's not independent. B and E are related in this way, which means that the whole thing, even though it looks like 6 independent PDEs for EX, EY, EZ, BX, BY, BZ, there's actually only 2 degrees of freedom that define the whole thing. Because once I have this, I can get the 2 degrees of freedom for B. Okay, so there's only really 2 degrees of freedom, not 6. Yeah?
Is it somehow related to polarization?
We'll get there. Yes, we'll get there.
Are you getting the 2 degrees freedom from the 2, so 2 for E and then 2 for B?
That's correct. But they're not independent. 2 for B are defined by the 2 for B. They're not independent of one another. All right, good. So, of particular interest is the situation where the time dependence is harmonic. Okay? So, of particular interest is when the time dependence oscillates with some angular frequency omega. Okay? We would say this is monochromatic. Because as we know, colors are related to the frequency of oscillation, and if it's one frequency, then it's monochromatic. Yeah?
So time dependence oscillates, is that saying like the time derivative itself?
I'll tell you what I mean by that. Okay? It's a little bit of loose language. What it's saying is, so, one way to write a function which oscillates as a function of time with frequency omega, any function like that can be written as follows. So we're going to use, and you're going to get used to, complex notation. So if the electric field is oscillating as a function of time with one frequency omega, I can always write that as the real part. Well, before I do that, because I don't want the polarization, as Omar alluded to, gets a little more complicated. Let's just say I have some function, which is a function of one variable and time, and I say that this function is oscillating at some frequency omega. I can write that function, if I like, as having some amplitude This is the most general function that oscillates. It has some amplitude, it oscillates with that frequency, and some phase. Every function that oscillates is a function of time with frequency. That's what we mean, okay? Which I can also write as a cos phi cos omega plus a sine phi sine omega t, right? Yeah.
So that's 3 degrees of freedom, right?
No, the degree, that notion of degree of freedom is not how many parameters, it's how many fields. So here I needed 6 different fields, here I only need 2 fields, that's what I need, right, here. But now I'm just talking about just trying to get some notation straight to say, let's just consider an arbitrary function that's oscillating as a function of time. It's some cosine function, has some amplitude and some phase, right? So this thing is, you know, some and there's some amplitude to this thing, and then there's some phase at which it is at time t equals 0. Okay, it's the most general oscillating function. I can write this function in the following way. It's equal to the real part of phi is a function of x. Okay, this is equal to the real part of something I'm going to call the complex amplitude of f e to the minus I omega t, where f tilde is equal to a e to the I phi. Okay, so is that clear that when I plug this in and I take the real part, I get this? How would you do that? Plug it in, I get the real part of f tilde e to the minus I omega t minus phi, right? And now this thing has a real part and an imaginary part. The real part, I mean, I could also write this as f tilde cos omega t minus phi plus I A. Thank you. If I take the real part of this is real, I get cosine of that. That's good. Alternatively, if I write this as cosine plus I sine, I see how that goes, right? So I can always write any, and this is really important, I can always write any function that oscillates with this time dependence as being a complex amplitude oscillating with e to the minus I omega t, and then I take the real part at the end, okay? And the complex amplitude contains the when written in a polar form, contains an amplitude and phase. Okay? Yeah.
It's just a sign convention that we put the negative.
Yeah, so that's a good question. Why do we put that? It's because it's right. And the reason in that, in a harmonic oscillator, if you might remember from your classical mechanics in momentum, position of momentum, and I start with something with some position and some momentum. So I pull the spring and I give it a kick. Okay, this is the angle phi from the x-axis. What direction does this thing rotate in space? It goes this way. It goes that way. You know, if I pull it out, it's going to go back, right? And so the phase goes to the phase minus omega t. That's why we write it as e to the minus omega t. But you're right, it's kind of then a convention, but we'll stick with it. Okay, with that said, that's true for every vector component. So I can write, if I'm looking for, I'm making one of my favorite words, an ansatz. An ansatz is just an assumed form of the solution, and we look for solutions that have that form. So we want to make the ansatz that we have monochromatic fields. So I'm going to say the electric field as a function of time is the real part of some complex amplitude that is going to be a function of position e to the minus I omega t. This thing here also, now the tilde I'm putting on the bottom because we already had a vector up there, and you can only have one hat and choose. Okay, so that's my assumed form. I'm assuming I have a monochromatic field, and then I plug that in to the wave equation. Okay, well, there's a number of things. I can look at Maxwell's equations now for the complex amplitude. So the way we do this when we work with the complex variables is this is the complex field, which in classical electromagnetism is a shorthand that helps us deal with monochromatic or oscillating fields much more conveniently than dealing with sines and cosines. It's much easier to deal with the exponentials, okay? And then at the end of the day, we take the real part, okay? And if we're dealing with linear equations, I can do that at the very end because the real part sort of commutes with the derivatives, okay? So what that means, for example, del dot E is 0. Well, that means that the complex amplitude satisfies that because there's no time dependence there. Similarly for B. And what about the Faraday law? What we have from the Faraday law, well, just a little aside, when we're going from in complex notation, every time we see a partial derivative with respect to time, I can replace that by multiplication by minus I omega, right? Bless you. And we see that, I'll just do it once and I'll never do it again. If we look at del cross E tilde e to the minus I omega t is equal to minus 1 over c d by dt b tilde e to the minus I omega t. Okay, everything has this time dependence. That's Faraday's law, just substituting in the ansatz for this time dependence. And when I apply that time derivative, the time derivative acting on that brings down a minus I omega. And they cancel on both sides. Oh, not there, because I haven't taken the derivative there. Here. So what we have is that del cross E complex amplitude is equal to plus I omega over C B complex amplitude. And similarly, del cross B complex amplitude, replacing the d by dt as multiplication by minus I omega. Okay. So now we've gotten rid of the time derivatives by assuming this ansatz. We got rid of the time derivatives. We just now have space derivatives in the problem. Okay? And the wave equation then becomes what? Well, the d by dt's get replaced by multiplication by minus I omega. We have it twice, so we get del squared minus c squared minus I omega squared p tilde is 0, or del squared plus omega squared over c squared d tilde is equal to 0, and similarly for b. everyone see what I did?
Excuse me, sir.
Yeah.
Divergence of E equals to 0, and divergence of E, is it E theta down?
Yeah, it's still there.
Understood.
No, other side, the other bottom, the other side of the bottom, it's still there.
Okay, theta, we have it down.
I'm sorry, can you ask the question again?
Yeah.
On this one?
Yeah, I'm talking about divergence of E, theta. Is it theta down? That is theta.
Tilde.
That's it.
Yeah.
The tilde. What I'm saying is, what I've done is I've expressed E in this assumed form. In some sense, I've separated the variables. I'm looking for solutions to Maxwell's equations that have this form. So I can do that by just substituting that assumed form into Maxwell's equations and then looking for their solutions. They will have this form by assumption. So I just assumed it had this form, and I say, are there solutions that have this form? If they do, then those are perfectly good solutions. Okay? So we've turned the wave equation into a PDE that's only the function of position, because the time dependence is given. The time dependence is oscillating like e to the minus I omega t. Okay? And this equation, by the way, is known as Helmholtz equations. And remember, I was trying to remember the name of the guy who first detected electromagnetic waves? It was Helmholtz. Okay? This is an equation, a partial differential equation, which we can solve, and we will. So each component of E and B satisfy the Helmholtz equation, but they're not independent and they're constrained. Okay? The divergence of that has to be equal to, each one has to be 0, and they have to be constrained in this way. All right, let me remember where I was going to head next on this. Oh yeah, okay, so firstly, to get the question, this is a complicated object. It's a vector that has, is a complex number, okay? So we write E tilde most generally in the following form. It's a function only of position. And I can think about that as, okay, it has some directions. That itself can be a complex vector. It has some amplitude, which can be a function of position. It has some phase, which can be a function of position. Okay? At this position, this is its direction, which itself is a complex vector. So this is the phase, the amplitude, and as was suggested, this is what we call the polarization, which in this notation can be a complex vector. We'll come back to that. The polarization vectors in this formalism are complex vectors, in the same way that in quantum mechanics, vectors in Hilbert space are complex vectors. Yeah?
The epsilon is a unit vector, right?
It's a unit vector in the sense, so this guy we're going to take to be minus squared is 1, which is E star E. Right. Thank you very much. Okay. Now, well, let's just take let's look for a simpler set of solutions to start. Let's consider the case where epsilon tilde is some E which is real. Let's start there, okay? Then the actual electric field as a function of time, which is the real part of E tilde e to the minus I omega t, since this is real, is equal to E hat E naught of x. This is real, because I've written, this is the magnitude in the phase, is equal to this times the real part of e to the I minus 5x, which is e cosine omega t minus 5x. So this is the sort of most general solution for monochromatic field that's oscillating at some time, depending on what its phase is and what its amplitude is, if I've chosen the polarization vector to be real. Yeah?
How come the polarization vector is not position dependent?
I could make such a thing, but I don't want to consider those terms, so yeah. So you're right. I could say the most general form is this. Okay, you're absolutely right. And we'll see that in the homework, so that's a very important point. I could have the polarization being different at different points. Let's say you could have a polarization gradient. Real and uniform. Okay. Okay, so let's continue. And let's consider a particular class of solutions that are what we call plane wave solutions. And the plane wave solutions are ones where the phase as a function of position has this form. Okay? So that I can say is the direction of K that's the direction, I'll call it E hat, along K. All right? For example, let's say this is the Z direction. Then the phase as a function of position is K times Z. Okay? Now, what we see, of course, here, if the phase has this form, that means that that the phase or the position dependence, in this case, if I were to write the electric field in this case, and moreover, I'm going to look for the solutions where E naught is uniform. Then my electric field, according to what we have on the other board, is the polarization E naught cosine kz minus omega t, from what we have over there. What we see from this form here is that at a fixed time, E is periodic in space. Okay? Because whenever this thing equals 2 pi, I go back to myself. And so what is the period in space? When this So the wavelength is the period in Z. So when K times the wavelength is 2 pi, I've come back to myself, which tells me that the wavelength of this is 2 pi over K. The temporal period is when omega times the period is 2 pi, or the temporal period is 2 pi over omega. Basic stuff about waves. Okay. So, if we go back to our complex ansatz, my electric field for a general plane wave is equal to the real part of the polarization, the amplitude, e to the I. Now, I could, if I wanted to, add some constant phase so that wouldn't change anything. It would just shift where the amplitude went to the highest point. So I'm gonna allow that. E to the I k dot x, e to the minus I omega t. Okay? I'm gonna call this E0 tilde. All right. So my plane waves here are the real part of E hat, E0 tilde, e to the I k dot x minus omega t. Those are plane wave solutions. What can we say about those plane wave solutions? Well, as we said, there are constraints. There are constraints given by Maxwell's equations. In particular, del dot E has to equal 0. Okay? So we have that the complex amplitude as a function of position here is E hat, E naught, e to the I, k dot x. All right? We also know that del dot E is 0. What does that tell me? The divergence of this has to be 0. How do I take the divergence of this? I have to take the derivatives, I have to do that. But here's the other trick. So what we said was d by dt, when I use the complex in time, became multiplication by minus I omega, right? Now we have the same dealy bob, but instead of space, instead of position, we have space, right? This is like e to the I kxx, e to the I kyy, e to the I kzz. And then I have to take the partial respect to x, or the partial respect to y, or the partial respect to z.
Multiplied by IK, whatever.
Exactly. So whenever I see del, I replace it by the vector ik. Because I'll take the partial derivative with respect to x, I'll get an ikx. I take the derivative with respect to y, I bring down an iky. Is that clear? So every component. So with that said, what does this equal? And when I plug in tells me is that K dotted into the direction of the electric field vector is 0. Okay. So, as we will see, this means that the field is transverse. I'll explain, remind you what that means in a moment. How do we see that? Well, so let's go back and write down again the real field. The real field is equal to that's the most general field we have with a constant amplitude, constant polarization, that's real. Okay. This is a wave that's propagating in space. That is to say, there is, if I were to write this, what I see here, let me write it in the following way. Let's write this phase over here. Let's, for simplicity, just say that this is propagating in the z direction, just for simplicity. Right? So this then is equal to kz minus omega t plus phi naught. Which is to say, I can write this as k times z minus omega over t plus phi naught. Okay. This over here is a velocity. It is in fact equal to c. We'll come back to that. So this phase is equal to k times z minus ct. What that says is that a point of constant phase is moving at the speed of light. Okay? That's to say, if I want this to be constant, I have to move with z equal to ct. Then this is some constant. I'm at the same phase. So a point of constant phase is moving at the phase velocity c, which is equal to omega over k. And what direction is it propagating in? The direction of k. So E sub k is the direction of propagation. How do we prove that the phase velocity is equal to omega over k? Where does that come from? Well, it comes from the wave equation. So what we have is that del squared right? That was the wave equation, or Helmholtz equation. And for the case of a plane wave, this was equal to right? plug in that assumed form. And now what do?
You put it in there.
I gotta apply the Laplacian to this. And how do I do that? Right. So this then tells me Laplacian is del dot del. But that means I just replace this by ik dot ik plus omega over c squared is equal to 0, right? Which tells me that omega squared over c squared is equal to the magnitude of k squared, which is k squared, which tells me that k is omega over c, or equivalently, c, which we said was the phase velocity from the wave equation, is equal to omega over k.
No, we're just working in the complex situation.
So, and if we have a plane wave, we have a relationship, we have these parameters omega and k. K is a vector. The direction of k is the direction of propagation. The wavelength is 2 pi over k. The period is 2 pi over omega. And the phase speed or phase velocity is omega over k. You must remember every single one of these things. You need to keep drilling these things into your mind if they're not there. These are very basic equations of wave physics. And those are the things you need to review for yourself. What's the wavelength? What's the frequency? What's the speed? How are they related? Yeah, Kristen.
Did I miss it? Did we take a Fourier transform?
We didn't. We are looking at a Fourier component. You can think about it as a Fourier transform, but they're intimately related, because if I know what the solution is for some Fourier component, well, I know the whole Fourier transform. What I've done, all I've done here was just said, let's look at the solutions that oscillate like this.
Because the derivative equations look very Fourier.
They're the same thing.
So, right?
They're exactly the same thing. Yeah, we'll talk about that next time. All right, let's continue with this a bit. So, what do we know about the plane wave? We know these things. We know that also that the direction. So what we've said is that direction of propagation is k, is direction of k. And the direction of E, which is E hat, is perpendicular to k, because E dot k is 0. Okay. So if I were to look at some instance of time at the electric field, if this is the z direction, the electric field is pointing in a direction perpendicular to the direction of propagation. And this is the wavelength. Okay? The electric field at every point has a different length given by the cosine function. Yeah?
Is there any significance to us using a hat for the field unit vector and an arrow for the direction of propagation unit vector?
Oh yeah, sorry.
Okay.
Yeah. All right, so that's E. E is perpendicular. What about B? B is determined by E. As we said, these are not independent equations. They're not independent equations because we've already expressed right over here, I can solve for B. From Faraday's law, we have that del cross E is equal to minus I K B. Right? For a plane wave, that means that I times K vector crossed into E is equal to minus I K magnitude B. Which means that B is equal to E tilde crossed into E sub K. If I divide this by its magnitude, I get the unit vector. And I change the direction, right? So, if we have K in this direction and E in this direction, what direction is B in? E cross B is K.
E cross B points in the direction of.
Oh yeah, that is true. Something screwed up here. Where did we screw up?
No, he was doing K cross E, you need to do E cross A.
Oh. Plus. Thank you. Phew! That makes more sense. K cross E. Yeah, good. K cross E is B, E cross B is K. Yeah.
Would it be sloppy for us to have said we know that the energy has to be flowing with the wave?
We don't know that. We have to derive that from Maxwell's equations. You know that because it came from Maxwell's equations.
We know that from pointing vector.
But we don't know that, but we haven't solved for the solutions of the plane wave, so we'd have to find what the pointing vector is for a plane wave, which we were about to do, and then we'll see that in fact the flow for a plane wave is in the direction of K. That doesn't follow from anything other than the solution. Right, so as was described here, this tells me that if I look at E cross B, that's E cross B, cross So as Tristan was saying, what we see here is that the direction of energy flow, which is given by the Poynting vector, is equal to so the direction of energy flow is K. What is the magnitude of B? Well, the magnitude of B is given by the magnitude of this, which is equal to what? If this is a unit vector, the magnitude of E itself. So in CGS units, the magnitude of B is equal to the magnitude of E for a plane wave in vacuum. Okay. Whereas you may remember is that B is equal to E over C from your SI units. Okay. That's because the Lorentz force law has a 1 over C in it. What else can we say? I want to talk, so this tells me for this, as we know, the B fields then are locally perpendicular, and this whole thing is moving along at the speed of light.
Just like you did.
And I have to speed up. And as I'm sitting here at a fixed position in space, what I see is the electric field going up and down, and it goes up and down with a period t or an angular frequency omega. Okay? So as it crashes through me. Why is this thing called a plane wave? Yeah.
Because the electric or magnetic field is confined to a plane of polarization.
So it's not that it's constrained as much. There is a plane here. It's the question of what we call a wave front. A wave front is a surface which has the same phase of oscillation. Okay, so let's just so here's the origin. There's some position. And I want to know what are all the positions in space at a given time that have exactly the same phase. Okay, so the phase, I'll call it capital Phi here, is equal to, or strictly phi, k dot x minus omega t plus some phi naught. And I want to know if this whole thing is a constant, what are all the positions in space which have the same k dot x? What are those positions in space? What surface is that? We have to think about this. So if I break up x as an x parallel to k and some component perpendicular to k, all the components that are perpendicular, all the positions that have the same x parallel but different x perp will have the same k dot x, right? So I'm saying that this is equal to the only component that is along k, the part that's perpendicular to it, and those points are a plane. They're the plane that's perpendicular to k. So there's a plane here where this is perpendicular to k, and everything on that plane has the same phase. And this plane, so what is really here, as Benny, you were sort of suggesting, is that at this z, there is an xy plane, right? And everywhere on that plane, I have the same length of the electric field. And these planes are propagating, okay? The electric field in each plane is different according to the cosine wave, and those planes are propagating. That's why it's called a plane wave, because the wave fronts are planes. Now, there's something weird about a plane wave solution, in that a plane goes on forever, which says the electric field is the same everywhere in x and y at a fixed z, and it has infinite amount of energy. Yeah. So, what is that telling us? There are no plane waves.
Approximation.
Plane waves are a mathematical, so this has plane waves have infinite energy. They're not physical. There is no solution in the world that is a plane wave. So why in the world do we spend so much time talking about plane wave solutions? Yeah. Yeah, but there's lots of easy things. We could just not do physics at all. Maybe that's just, yeah.
Same reason we talk about infinite plane capacitors, because if we get close enough, it's a good approximation.
Yeah, so everything is about idealizations to which some things are good approximations. I'm from the Flat Earth Society because the Earth is pretty flat. Well, not in Albuquerque, but if I went to Kansas.
Just different plane, right?
Yeah. And so there can be good approximations to plane waves. If I have a laser beam, then it's actually a beam. It doesn't extend forever, but it's got a beam profile, and it might be, some few microns. And if I'm only looking over a few nanometers, it's pretty planar. So a plane wave is an approximation to physical solutions, but there's another reason.
Don't they consider the basis?
Exactly. So it's a mathematical construct in the same way that delta functions are a mathematical construct, which allows us to think about, as Tristan, as you described, think about Fourier. So the plane waves represent the Fourier components, both in space and time, of true fields. And so and that goes back, so I was teaching that, yeah, they're easy. And so it's an easy basis to think about, which we can then construct arbitrary solutions out of superpositions of plane waves. So it's important to understand these sort of, building blocks that we yeah.
Did we so I see that how the plane waves has infinite energy just intuitively. Did we break any constraints regarding our equation in the solution?
No, I mean, there are solutions, the solutions to Maxwell's equation say nothing about whether they're physical or not.
I see.
So the fact that the integral over all space of this is infinity doesn't violate Maxwell's equations. Maxwell's equations doesn't say anything about this kind of constraint. That's a constraint that follows more from, our just empirically. We know, the question would be, what is the source of a plane wave? The question would be, how can I radiate something that is a plane wave?
Big plane.
Make it change.
There is no, I need an infinite energy source to create an infinite energy field. Mathematically, they're perfectly good solutions to Maxwell's equations, but there's no initial condition I can start with, which would then generate a plane wave. We can generate something that's close to it, we can create something which is a spherical wave. And again, on the Flat Earth Society, if the radius of that sphere is very, 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 very big, then locally it looks like a plane wave. So the sources are spherical waves, they're things that are confined, but when they propagate out, they look like plane waves locally. Donald, yes, we're kind of running over, but I'm
Yeah,
happy.
what's wrong with having, aside from the non-physical part, wouldn't an infinite plane that you
Yeah,
move?
yeah, but that would take an infinite amount of energy.
Because fields carry energy, and so,
I mean, so we're gonna have a problem, you know, here I am, I'm my protester. I have a big sign, and I'm shaking it up and down, and it's got a surface charge on it, and I shake it up and down. If it was an infinite plane, it would radiate a plane wave, but it would take me an infinite amount of energy to do that. But we're gonna solve that problem, just because it's a nice problem to solve mathematically. Radiate the wave, radiate the wave. Yeah. All right, we'll end on that note. Have a good